So we'll now start the last video in this series that describes our representative data analysis pipeline. And here we're going to create some figures and do some very basic statistical analysis. So technically we've already done some stats because we just fit, we performed nonlinear regression in the previous video. So that's one form of statistical analysis. And here we're going to do some simple t-test, which is something that you may be more familiar with if you're just starting out with data analysis. So what we want to do in this figure is that we're going to try to, or this video is we want to create publication quality figures. Okay? And so in other words, we want to generate a figure that once we save it, it's something that we can submit directly to a journal. Typically, at least for me, most of my career, I spent a lot of time making figures in MATLAB, exporting them to as a whatever file, PDF, importing them into Illustrator, changing the fonts, rescaling the figure, changing the line thicknesses, and doing all sorts of things manually. That's a huge waste of time. And so what we really want to be able to do is to take control of our figures and define our figure properties and settings in code so that not only is it reproducible, but it just really streamlines our analysis and communication pipeline. All right, so again, in the script, you can read through the comments, and that describes exactly what we'll be doing. So what we're going to start by doing is loading some data and just generating a blank figure. So let me actually navigate back to the folder here. So just as a note, if you receive an error when you try to run your code, it's probably because you're trying to move into a directory that's not a subdirectory. In other words, you're already in this folder. So just make sure you run these scripts from the top folder of this directory. All right, so let's try this again. All right. So as a reminder, the figure command will open a figure window in MATLAB, and now we can do all sorts of things within that window. So here, one of the things that I'm doing is just finding all the cases up front where we decided not to fit our data. And I'm using a function called isNaN, which just checks for NaN values. And here I have what's called a tilde. So this gets all the values that are not NaN. So in other words, all the values that we actually fit or derived from the data that we fit. So let's walk through example bit of code. So really there are just sort of 2 or 3 pieces to this code. First is that we're going to use subplots in MATLAB, where again the subplot specifies the number of rows and columns, so the number of rows and columns in our figure. And next we're going to use plot, which is just the basic plot function in MATLAB, where here is where we define what we're going to plot, so our first input. And in this case, it's going to be my coefficients. Actually, let's just run this part of the code. Okay. So if we open our figure, what you'll see is some data points. It's not very informative, but some lines connecting those data points. So one question is, well, how did we do that? What we did was we defined a matrix here. So this matrix contains the coefficients for the slow, our a slow parameter, and the true parameter. So what we used to generate the data back in the first video. So if I highlight, copy this part of code, I can then paste it in the command window, press enter. And so you can see here that we have 17 columns corresponding to our, I'm not exactly sure why there's 17 and not 19. There's an error somewhere in the code. But for each participant, we have the fit value that we extracted when we fit the model to the data. and that's the top row, and then the bottom row is the actual value. So you can see that they're often pretty close, but not always, right? And this is just a really helpful way to validate any kind of model fitting or parameter estimation in your own experiments. Generate simulated data that has properties that are similar to what you're going to collect. You write code to process those data in the same way you would real data, and then try to estimate the parameters that you use to generate the data. Okay? As an aside, like we've recently found in some studies that when you try to fit certain types of models and estimate parameters, you really do a poor job of estimating the true parameters, right? You can get results from your analysis, but they don't at all reflect the real world. That's another discussion. Okay. All right, so we're going to plot. So for our plot, we have our 2 by, in this case, 17 column matrix, where each column is going to be a set of points, a pair of points. And then we connect each of those pairs with a solid line, and we represent the markers as an open circle. Here we specify our line width as 1. We specify the color of the data points, so the outline, as well as the face color, so what we fill in. Okay. So in this case, we have our we use something that's almost black for the outline, so we have 0.1 for all the RGB values, and then a sort of perfect gray as the face color, so 0.5 for all the values. Okay. So that's step 1. So we've just put the data on a set of axes. Now this isn't really a very useful figure. It's not aesthetically pleasing, I would say. You generally don't want to have data points on the axes, so we want to add some cushion there. There's no need for a tick mark at 1.5, right? And we want to label these as being the estimated value on the left and the true. Okay? So again, these are all things you might do in another program, but you're learning MATLAB here so that you can take advantage of the tools available, functions, and so on. And what we're going to do in this case is we're going to use set to take our current axis. So the first input here is our GCA represents our current axis. We're going to specify our X limit, the X tick marks, so where we want the ticks placed, the X tick label, which is what we want, how we want to label those tick marks, our font size, the general line width of our figure, and we're going to add some text as well. Okay. So now if I hover over all this, evaluate, now I can see that this is a much better figure. Each of my groups of data are labeled clearly. I have a Y label and a panel label. This is something that I was very proud to figure out how to do a couple years ago. So you can even add panel labels to your figures so that you literally have to do almost nothing in an external program. So for those who are interested, so this label I generated using the text command. And so for the text command, you just provide an X and Y value, the text, and then some properties. So here, if I go here, this is something that you should try to figure out on your own. But what I'm doing here is, making the text a function of our X limits. So the text is placed on the graph or on the axes relative to the X and Y values. So for instance, if my X value is less than the minimum on my axis, the text will be placed to the left of the axis. Similarly, if my Y value here is larger than the largest value that's plotted on the axes, the text will appear above. Okay. So you can kind of play around with that in your own code to automatically label your figures. So we're going to do the same thing. So this was for our slow coefficient. If I were to rewrite this code, I would sort of just write a function that does this because I'm repeating code here. So we have our slow rate, then our fast coefficient and fast rate. So let's just do all that. And that actually is something that would be a good exercise, is to take this code and create a single function that plots data on a specified axis and sets parameters and so on. So here's our final figure. You can see it's decent. We have a case where we have a pretty poor estimate relative to a true value, so it skews the figure. And we can think about other ways that we might want to represent those data. So finally, we're going to perform a set of t-tests. Well, I guess a couple more things. So one thing we might want to do is to use a t-test and compare the estimated values to the actual values. So let's just do this. And so to do that, what we're going to do is take, in this case, our estimated values, so our coefficients, as the first input to our t-test, and our true values as the second input to our t-test. MATLAB has a statistical toolbox which has most statistical functions or procedures that you might want to use, and highly recommend spending some time to learn find your way around that toolbox. So here we're performing a paired t-test because we want to check for each participant how, is there a systematic difference between their estimated and true value. There are other ways we could choose to do this analysis, but this is pretty straightforward for our purposes. So when we run our t-test, we will get H is just a 0 or 1 that corresponds to whether or not we have evidence to reject the null hypothesis, and then P is our p-value. So I can highlight this block of code, evaluate, and if we go back to our main command window, I'm going to clear my console, so CLC, and we can see all of our H's are 0 and our P's are all pretty high. Okay. So in this case, this will say that the null hypothesis would be that there's no difference between our actual or our estimated and original parameters. So if our p-values are quite high, then that means that there's not sufficient evidence to reject the null. Okay. You could do other kinds of tests of equivalence as an example to directly test if these values are approximately equal. Okay. So I said that was almost the last thing. The actual last thing that we'll do is save our figure. So first we're going to set the size of the figure. So you can see how it shows up on my screen here. I'm going to run this line of code. And I see it sort of moves, and there are just minor changes. And as I think you may have already seen, we're going to now export our figure in one format. Here is just a standard fig file in MATLAB, and then we're also going to save it as a PDF. So I'll highlight this, evaluate the selection, go here, and now I see my two versions of my figure. Okay. So I can open the MATLAB figure here, and I can edit that if I needed to in MATLAB, and then I can open my PDF in Acrobat, Illustrator, or whatever other program I might use to view and modify PDFs. So hopefully that gives you a good overview of how you might set up a data analysis pipeline. Maybe there are some, if you've already done this before, hopefully there are at least one or two things that you've learned that will help make your data analysis process more smooth. And so we'll have a few other activities that we have planned for the final couple of weeks here to really get you even more experience dealing with open source data sets.